Cool. Sounds like it's going. Okay, well, hey everyone. Welcome to the third Computational Biology Skills Seminar. We're really excited for you all to be here. It is strange times that we're living in, but I'm glad that we can all get together over Zoom and learn something new. So today we have Alyssa joining us, and she is a graduate student in the EECS department at Berkeley. She's co-advised by Nir Yosef and Anthony Joseph. And she does a lot of really cool computational biology work, trying to model how proteins called transcription factors bind to certain regions in the DNA and activate transcription responses under different cellular stresses. And so she works with a lot of big data sets, and she does a lot of developing her own software packages. And I remember talking to her last year about how frustrating it was to get something up on Conda and actually publish something with pip. And we were like pulling out our hair over this. And unlike me, she actually figured out how to do it. And so I'm really excited to hear from her, and I hope that you all are as well, about her trials and tribulations through the netherworld of publishing reproducible code with Python. So she's got tons of really great tutorials linked up here. So you can just follow along. And without further ado, I'll let Alyssa take over and lead the seminar.
Great, Matt. Thanks so much for the introduction. That was awesome. So hi, everybody. I'm Alyssa, and I'll just be doing a tutorial today. We'll be talking about a ton of different components of how to build a Python package. But first, before we get started, I would recommend that you get some of the material that we're using for today's tutorial. You don't have to pull the code. That is completely optional, but at minimum, I would highly recommend that you can navigate to the tutorial link, which can be found on this slide, or it can be found in the chat. So just make sure to pull that up. I'll be very closely following that, so you can also reference it in the future if we don't get to everything today. So the first thing I wanted to know from you all is how comfortable you are actually building packages. So if you haven't taken the poll already, you can go to this link, which is also in the chat, and fill out the poll. We'll be having some little poll questions as the tutorial goes along. But some of you have already filled out this poll. So my question for you is, how comfortable do you feel creating and publishing a Python package? So it looks like the answers are coming in, which is awesome. Thanks for filling this out. But it looks like a majority of the people today are beginners. So have never built published a package before, which is really exciting. So we'll be going everything at a super basic level. So don't worry about that. That is excellent. So I'm going to navigate away from this slide. So if you do need to find any of the links, remember they're in the chat. You can always go to the CCB Skills seminar page and find all the links there. Okay, so what are we building today? So we're building a very simple tool called MapQTools. And MapQTools is a package, more like a toy package, that plots the mapping quality distribution from an input BAM file. So say you have a file containing genomic alignments. This could be a BAM file or a SAM file. What our package will do is it will pull all of the reads out of that file and just collect the mapping quality statistics. So in this example on the slide, we have a plot that we've generated with our tool. It's showing the distribution of mapping quality scores across a small part of the genome from a BAM file. So by the end of this tutorial, we'll be able to generate these plots from Python and from the command line using the package we've built. Okay, so today's tutorial is outlined in the documentation I've provided online, but just a little overview of what we'll be talking about today. We'll first be talking about the project setup and the directory structure. This is all in the GitHub I've provided, but we'll just be going over it on my own computer. You can follow along on yours as well. We'll next be talking about creating command line scripts. This allows users who use our package to be able to call MapQTools from the command line without having to write a Python script to use our code. Next, we'll be talking about unit testing and continuous integration. This basically allows us to make sure that when we edit our code, it's functioning as we want it to function, but we can automatically test our code as we and others submit pull requests to our code base. Next, we'll be talking about how to upload our package. And we'll be mostly talking about uploading to PyPy, the Python package index, and Bioconda, which is another venue in which we can publish our packages. Finally, we'll be talking about adding documentation and publishing documentation so that people who use our tools can read our documentation without bugging us all the time with questions on how to use the package. So this is just a highlight of the slide I showed before, but just make sure that if you're interested in following along, you can get the code and follow along on your own computer. These links are all on the CCB skills page, so you can find them there. Okay, so I'm gonna go ahead and pull up the code base so we can just take a little look through it. Okay, so here's our Python package, which we built today. If I open up this directory in my favorite text editor, I can go ahead and see all the code I have. So in summary, within our package, we have the following items. We have some modules, we have some installation and build scripts, we have unit tests, test data, and then documentation, which we'll go through at the end. So let's first take a look at the basic directory structure. So I have this directory, plot.mapq, which contains all of my package code. So let's navigate into that subdirectory. So what I have here is within my package, I have what's called modules. And modules are individual Python files, which can contain constants or functions or any other information you'd like. So in this very simple package, we have two modules. We have a functions module, and we have a plot.mapq module. Both of these can be imported in Python once we install our script, and we'll see that in a little bit. The next important directory we have here is our test directory. Our test directory contains all of the unit tests that we'd like to test our code. So I have a count mapq test function that just contains two simple tests that will run in a little bit. Finally, you might notice this init.py file. So init.py files are required in package directories for Python to treat that directory as a package. So without the init.py file, Python is unable to identify that plot.mapq is a package. So if there's any directories you'd like for Python to consider part of your package, make sure you have this init.py file. So most simply, this can actually just be an empty file, but it can also include code that you need upon initialization of your package. So you could have a constant in here that defines your mapq cutoff, or any other constants that are deemed necessary for the package. A next important file we have here is our setup.py file. And this is the file we use for building and installing our package. So you can see on the first line of this file, we import something called setup tools. And setup tools is basically just a library for facilitating and packaging different Python projects. So what we can do is we can define the setup of our package using setup tools and define a bunch of different information that's important to our package. Some of this information includes the name of our tool. This could be any name of your package that you'd like. We have our package version. We also see we have required packages. So here I have a list of all the dependencies that our package uses. And this is important because if a user is installing your package, you also want the dependencies to be installed as well. So this is telling setup tools what our dependencies are. There are also a lot of other meta information about author information and the description of our tool. We'll come back to this line in a little bit, but we can also define a directory for where we have scripts for our packages. And we'll talk about this more in the command line section of our talk today. Okay. So last but not least, we have this subdirectory called docs. And this is where we'll put all of our documentation that we can then publish online for users to read. And we'll come back to this section in a little bit. So other important files. So at minimum, we have a README that tells users what our tool is and a little bit about it. That will show up on our GitHub page and on the Python package index when we publish our tool. So it's always important to have a README file that contains information of your tool. You might also notice a license file. License files are extremely important because they define how users can actually use the tool. So in this example, we have an Apache license, which I've just chosen arbitrarily. Most of my tools, I use an Apache license, but there are other common licenses that people use, such as the MIT license. Finally, I've included a make file. And this just allows us to easily call some of the things we need to build and publish our package. So for example, if you have the code downloaded, we can go ahead and install our package in editable mode. So to do that, we can type make develop. And that will call this line of our make file, which will go ahead and install our package in editable mode so that we can go ahead and use it. So now if I go ahead and start my Python interpreter, I can import my package as follows. Okay, are there any questions so far? Great. Okay, so given this really basic bare bones structure, users can start a Python interpreter and use our code. But what I mentioned at the beginning is we would actually like to have a command line script that allows our users to run our code straight from the command line. So users should not just be able to run our tool from Python, but we'd like it to be accessible by other scripts. So what we've included in our code is a file called plot-mapq in the bin subdirectory. And this is just a really simple script that allows users to run our tool from the command line. Additionally, we'll let setup tools know about this script. And this way, when we install a package, it can be accessible directly from the command line. So let's take a look at that script. So if we navigate into our bin subdirectory, we have a script called plot-mapq. So this is an extremely simple script. Basically what it does is to tell the interpreter that we want to run our Python code, and then this is all Python. So all we do is we import our plot-mapq library, and then we call this main function. And all this main function does is take in command line arguments to run plot-mapq. So you might be wondering, okay, well, where is this main code? If we navigate into the module that we've specified here, plot-mapq, we can find the main function that we're looking for. So let's actually try this out. So if I've installed my package with pip install -e, so this is a command we've run before, I can then actually go ahead and use my command line script by just simply typing the name of the script. And we can see, make that a little easier to see, we can see that we have the command line script, and it's saying we need some command line arguments. So we need an alignment BAM file, we need the name of our sample, and we need an out directory in which to save the image. So you can go ahead and run that if you have a BAM file on hand. There's also some test data in the test data directory. So you can run with that. So I'll go ahead and type plot map Q. And we'll use our mouse chromosome, mitochondrial chromosome BAM file. We'll call this our mouse sample. And we'll just make an out directory in which to save it. Okay. So it looks like it processed some reads. If we look at the out directory in which we've saved the data, we have two files here, a PDF, which is our image, and then a tab file that has the scores. So you might be wondering, how does Python know that when we type plot map Q that it should be accessing the script in our bin directory? The answer to that is actually quite simple and can be found in the setup.py file. So like I mentioned before, setup tools allows us to specify scripts that can be run from the command line. So within our setup script, we can just specify a scripts equals and then specify the location of the different scripts that we'd like setup tools to install when we install the package. So anything in this list will be accessible from the command line when a user installs our tool.
Just a quick question.
Yeah.
Which of these arguments are optional and which are mandatory for the setup tools?
That's a great question. So the name and the version are definitely mandatory. Classifiers, Python requires the URL and the description information, as well as author information, are all optional. I'm not quite sure about the install requires. I believe that is optional as well. But you can find that on the setup tools website. But at minimum, you should have the version and the tool name.
Okay, thank you.
Great question. Okay. Any other questions? All right, so next we're going to move on to talk a little bit about unit tests and continuous integration. So we looked in our package already, and we have a couple of unit tests. So we're going to see how those work, but then also see how we can really run those unit tests every time someone makes changes to our code. So what is the purpose of unit tests? Well, unit tests just ensure that our code is functioning as we expect it. It is super easy to start a new project without unit tests, but I guarantee you it will bite you in the butt eventually. Let's say you have an undergrad or a young grad student that you'd like to take on the project. You would like to know that the code they're adding is not changing the functionality of the code that you've added. So I highly, highly recommend making unit tests as the first code you add to your repository. Very, very, very important. So we can make unit tests, and that's all fine and good, but what we would actually like to do is run the unit tests, preferably every time someone changes the code, so we know whether or not updates to our code are actually breaking things. So how do we do that? So we can actually use something called continuous integration to run our unit tests automatically, and actually for free, which is a super great tool. So if you would like, there's a poll about continuous integration. So you can navigate to the same link that you previously filled the poll in and just answer the questions. And while you're answering that poll, I'm just going to tell you a little bit about the continuous integration that we chose to use in this tutorial. So in this tutorial, we're going to use what's called Travis to run our unit tests. So Travis, we choose specifically because it's free for public repositories. So if you have a repository on GitHub and it's public, not private, it will be free. And then you can additionally pay to run your tests on private repositories. So the great thing about Travis is it's super simple to set up, and it automatically runs our unit tests on new pull requests and whenever the code is updated. Okay, so let's take a look at the survey. So looks like, oh, someone filled out the license. That's interesting. Awesome. And then if we took a look at continuous integration, it looks like many of you have not used continuous integration before, which is perfect. Travis is great for beginners. There's also some other ways to do continuous integration. One is called Jenkins. Wouldn't recommend it unless you have a full-time engineer. But Travis is really great. And it looks like some of you have used Travis, so that's really exciting too. So you can correct me if I am wrong with anything. Okay, so let's first take a look at the unit tests that we've implemented, and then let's go ahead and look at how we can run these unit tests on Travis. So like I mentioned before, we have a test subdirectory, which contains unit tests to run. So our unit test uses the unit test library to just go ahead and implement some really simple tests. So more importantly, we want to know how to run these tests. So we can very easily run these tests locally using a tool called PyTest. PyTest is a tool that iteratively searches our packages and finds these Python files that are most likely test files, and then runs these tests from the command line. So if I open up my make file, I actually already have a directive for running the tests. So what this does is this runs Python and calls our PyTest, and then runs all of the tests in our project. In this case, our tests are just our whole directory, and then PyTest can go ahead and search and automatically find all the tests it wants to run. So if you're running this on your own computer, make sure you have PyTest installed. But to go ahead and run the test, we can just go ahead and run make test. And those tests are running, and it looks like both of our tests pass. So we have 100% pass rate, and 2 of those tests passed. Okay, so that's how we run our tests locally, but how do we use this Travis and continuous integration? So once we have added our unit tests, we can automatically run tests every time our code changes. And to do this, we're going to use Travis. So the first thing we want to do is open up Travis on your web browser. So there's a link to Travis in the tutorial, but you can go to travisci.org, excuse me. And let's see, I can post this in the chat. Okay, so it's posted in the chat if you're interested in taking a look. So the first thing you'll have to do is make an account if you don't have a Travis account and you're interested, but I already have an account, so I can just show you mine. So we see at the top, I'm logged into my account, but we have this little GitHub symbol, meaning that Travis is linked with my GitHub. And when you create a Travis account, it automatically asks you to link a GitHub with Travis, so it's super easy to do. So once I have my account linked, it shows me all of my repositories that I have in my GitHub. I have a ton of repositories, but I'm not running Travis for all of them. So let's look at our top 2 projects, which is the Comp Bio seminar, which has a check mark, meaning the tests are passing and that the tests are set up to run on Travis. So we'll go ahead and click on this. And it looks like my tests are passing, which is awesome. So if we scroll down, we can see that Travis had ran the 2 tests we saw in the command line, and both of those passed. Now, if one of you were to make a pull request to the repository, these tests would then run automatically. So if you broke anything, hopefully the tests could pick up the code break. Okay, one last catch about Travis. You might be wondering, well, how does Travis know how to run my tests? That can't be automatic. So no, Travis is not magic. So we do need to give Travis a little bit of information to tell it what are my dependencies and how to run the tests. And so that's actually not too complicated either. So to run Travis, all we have to do is provide a .travis.yaml file. And this file contains information on the dependency my project needs and how to run the unit tests. So for a Python project, this is very simple. All we had to do is specify the language, which was in Python, We specified the Python version. We specified make develop, which installs the dependencies that our project needs. And then to run the tests, we just specified make test, which goes ahead and runs these unit tests we're seeing on Travis. So in summary, all Travis requires is an account that's set up to your GitHub, and then a .travis.yaml file that's in your GitHub so it can figure out how to run the tests. Other than that, everything should be pretty much automatic and run as needed. Okay. So next we're going to go talk about how we actually upload our packages. We're going to be talking about uploading to PyPy, and we're going to be talking about uploading to Bioconda. But before we go into that, does anyone have any questions? Okay, great. So the first topic we'll talk about is uploading a package to PyPy. So like I mentioned before, PyPy is the Python package index. And if we actually navigate to PyPy, we can search different tools and then download them accordingly. So I've actually already uploaded my tool. So I can go ahead and search it and find it in the search. And here you can actually see PyPy took the README that we have in our repository and provided information about the, our package. We also have release history, so we've only published one package so far, but we can specify different versions and then publish packages as we update our code. Finally, we have this tab called Download Files. As we'll see in a minute, when we package our project for distribution, it will create different files, and these are the files that we'll create locally before actually pushing them to PyPy. Okay, so in order to publish our package, we need to do a couple different things. First, we need a PyPy or a test PyPy account. If you're going to be publishing your package, let's say for a publication or for general use, you definitely want to create a PyPy account. If you just want to play around and test out how to publish packages without, before actually publishing them permanently, you can use what's called test PyPy. And test PyPy just allows you to play around with publishing packages without them being super serious. And so that's what I'll be using today because this is just a tutorial. So once we have an account, you can go ahead and build the package locally, and we'll talk about how to do that. And so once we built our package, we can then upload those files to PyPy, and then it will be readily available by anyone who wants to use it. Finally, not required step, but we're gonna go ahead and tag a release on our GitHub account, just so people know that we have created, pushed our package with a new version. So let's go ahead and actually build our package. So we have to go ahead and build the distribution code so that we can go ahead and push it to PyPy, and those files can be accessible for download. So if we go ahead and open up the make file, let's see what we actually have to do before we push to PyPy. So you may notice that I already have a directive that does everything we need to push our code to PyPy. And so this is what this does. The first thing we do is we clean our directory. This is going to delete any files that we need to rebuild before pushing. The most important line here, though, is how we actually build the distribution code. So we're going to go ahead and use our setup.py file to build our distribution. So we're going to build two different distributions. So we have sdist and then bdist wheel. So what this does is these actually just build two different distributions. And when a user installs your package, depending on the environment they have, it will either take the distribution from the wheel or the distribution from Estes. And so what do I mean by that? So if I call this line, so Python setup, and I'll build my Estes, and I'll also build my wheel. So we'll run that. So if we look in our directory, we now have a subdirectory called dist for distribution. So let's take a look at what's in this subdirectory. So here we have two files. We have a wheel file and we have a tar.gz file. So these are just two basic distributions that contain the same information. And like I said, when a user is installing your package, based on the environment they have, it will install one of these files. Okay, so I'm gonna go ahead and run my make PyPy. And so this is gonna go ahead and clean my repository. Any remaining files that I have, it will delete. This will go ahead and build the distribution code I need to upload to PyPy. And finally, this will actually upload my code to PyPy. So how does that work? So we actually use a tool called Twine, which uploads our package that we're creating. And so what this allows us to do is Twine allows us to check that we have all the required files that PyPy requires before publishing a package. So the first thing we can do is we can run twine check. And this will just make sure we have all the required packages we need for uploading to PyPy. So once Twine has ensured we do indeed have the files we need, we can use Twine to upload our distribution subdirectory to PyPy. Here I've specified a repository URL that's going to upload to test PyPy. However, if you wanted to publish a real tool, you don't need this. So this is just to play around with, so it's uploading to the test PyPy repository. Okay. So if you are indeed playing around with this on your own computer, you may note that I've already published MapQ tools on test PyPy. So in the future, if you'd like to try to upload this by yourself, you can go ahead and go into your setup.py file and change the name to something unique. So if you're interested in uploading this yourself, you can change this to something like your name or a random identifier. Otherwise, you won't be able to upload it because I already have. So you can go ahead and do that. So then to go ahead and upload, I'm just going to type make PyPy into the command line. Oops. Make PyPy. And we can see that it is building the distribution code we need. Twine went ahead and checked that we have the files that we need. And now it's trying to upload my code. So I can go ahead and type my test PyPy username and password. And if the credentials were correct, it would successfully upload to testpypy.org/legacy. Okay. So in summary, in order to publish, all you need to do is you need to build your distribution code with your setup script, so Python setup. And then you can use Twine to check and upload your distribution code, and then upload to PyPy using your username and password that you generated on their website. Okay. So like I mentioned, I've already published MapQ tools to our test PyPy, so we have all of these files available that we've generated, and this is an older version, but all of the files that we generated, and we only have one version. Finally, if you wanted to install the tool from test PyPy, you can use the line specified on the test PyPy page. So pip install, and then the name of our tool. Okay, finally, we would like people who use our code to know that we have published the code for use. So one thing I always like to do after I've published a version of my package is create a release. So releases are on GitHub, so you can do this from your GitHub. And basically this allows anyone who is looking at your code repository to know which versions are available and what they're fixing. So let's take a look at our releases. So we can click on release. And it looks like we currently have one release. This is the very first version of our code. And we have some meta information about that release. So I can go ahead and make a new release. And let's say I've made a new version. We'll call this a new pre-release. We'll call this 0.0.182 just for a new version. And I can call this, I can call my release anything. And then I can put information of the new package I've published. So let's say we have a bug fix. So we have bug fix. Now works from the command line. Or other information that this specific version is providing. You can specify any information here. You can go ahead and publish your release. And once you publish this release, it will be available for anyone to see on GitHub. So if someone is frequenting your GitHub page, they know that you have a new release out, which might be exciting for them. Okay. So any questions before we move on about PyPy? I do want to reiterate that there is a lot of information into this tutorial, but what I like to say is once you've built one package, you've built them all. So you won't have to remember anything I say today. All you will have to do is go to the GitHub repository that I've already built and use that as a cookie cutter for future packages. So don't worry about remembering everything we talk about, just remember that this is all available online. Okay, so next we'll talk a little bit about adding a package to Bioconda. So if we've already added our package to PyPy, why would we want to add it to Bioconda? So for most of you, PyPy might be sufficient. PyPy is really great for publishing really simple Python packages, and anyone can install your packages if they use pip. So you can always pip install whatever package that you've uploaded to PyPy. However, Conda allows us to package more complicated projects. So let's say we have some data we need to download from S3, or let's say we have some Java code or some C code or some more complicated dependencies. This becomes a little hard to manage in PyPy. Additionally, users aren't always using pip. So if a user is using Conda, it might be nice for them to install your tool through Conda instead of just PyPy. So Bioconda is just the bioinformatics channel for Conda. So Bioconda contains a ton of different tools. You can Conda install RSEM, you can Conda install BWA mem or star. So there are a ton of tools that are published on Bioconda that are specific for bioinformatics. So another huge plus of using Bioconda to publish your package is that they automatically build Docker containers for you every time you publish your package. So for those of you who aren't familiar, Docker is just a way to containerize your code. So people can pull a Docker container that contains all of the dependencies your package needs. And you can also include data so people can just run your tool right out of the bat without having any issues with dependencies. So Bioconda gives you that extra bonus of automatically making Docker containers without you having to worry about it. So we're not going to build We're not gonna put our package on Bioconda today, just because it's managed by people like you and me, and I didn't wanna waste their time on a test tutorial. But what we will do today is just look at an example that has a very simple Bioconda package online that we can use as a template in the future. And this tool is called PyRanges. Okay. So here we are on GitHub, and we are at the Bioconda repository. So in order to create a Bioconda package, you will have to create what's called a recipe with the code needed to generate your Bioconda package. So here we're looking at the recipe specifically for PyRanges. And so there are two files we have that are required by Bioconda. The first is a license file. We've already talked about including a license file, so you can copy and paste this from the license you have in your repository. The more important file here is this meta.yaml file. This is going to specify how Bioconda builds your package to publish it on Conda. So let's take a look at this file specifically. So this is a YAML file that contains a couple important information. The first of which you'll see is the name of the project and the project version. This is required by Conda to publish. Additionally, you'll see information on what Bioconda needs to actually build your project. So PyRanges is very simple. It was already published on PyPy. So all we do is specify this source code, which is the location in which it's published on PyPy. And so all of the build does is it goes ahead and installs the code from PyPy. So if you've already published your code on PyPy, all you need to do is modify this YAML file and point it to your PyPy directory. So this will just go ahead and install the distribution code from PyPy, and Bioconda can do that accordingly. Also, there's some meta information here about the tool and the authors. We can also specify any dependencies we need. So PyRanges is a Python project, so it needs things like pandas and other Python requirements to build the package. So if you are building a Python project, I highly recommend you use PyRanges as an example if you would like to push something to Bioconda. So I already mentioned Bioconda has that additional benefit of automatically building Docker containers. So these Docker containers are published on Biocontainers. So this is just where the PyRanges Docker container is available. So if you wanted, you could use Docker with the PyRanges Biocontainer. If you publish your own tool on Bioconda, you will also have your own Biocontainer for your tool. So that's really exciting. Okay, so we are running at the end of the hour, but we just have one more topic before we go. And the last topic we'd like to talk about today is adding documentation to your tool. So documentation is super important, especially if you're going to have lots of users. It's really important that you lay out very directly how a user can install and download your tool, and then how the user can use your tool. This will save you a lot of time in the future from answering a lot of questions on GitHub, maybe about how to use your tool. Even if you're just using your package within the lab, I think this is also a good thing to do if other grad students are using your package, such that they can reference it maybe after you graduate as well. So we're going to talk about how to build documentation locally, but we're going to want to publish that documentation. So we're going to use a tool called Read the Docs, which just automatically builds our documentation for a project. So let's take a look at our documentation. So we have this folder called docs, and this is going to contain all of the documentation we need. If we go ahead and open this directory, there's what's called RST files. RST is a restructured text file that is just the format that we use on Read the Docs. So you can go ahead and write an RST file. We have a header here for the introduction, and this is just some of the landing page of our documentation that users will see. So we also have all of the documentation from the tutorial that you may or may not be currently following along with. And so this is contained in the tutorial subdirectory. So we talked about the command line today, we talked about conda, now we're talking about documentation. Okay, so there are a couple important files here that you'll need in order to build documentation. The first is a requirements.txt file. So this requirements file just contains all of the Python requirements that Read the Docs needs to build your documentation. We use a tool called Sphinx to automatically generate our documentation. So we include that in our requirements. We also have some other requirements, such as a template to view our docs nicely, so we will use that as well. Another important file we have here is called our conf.py file. So if you use Sphinx, there are a lot of configuration files that you can just copy and paste from the internet, which is I think what most people do. But this conf file just is all the configuration you need to use your docs. So at minimum, this file actually requires very little work, but you can add and remove from this file to really make your documentation custom as needed. Okay, so let's go ahead and build our docs locally. So I'm going to go ahead and navigate into my documentation folder, so cd docs. And I can go ahead and I have a make file here that lets me build my documentation locally. So I can do make HTML. And this will go ahead and create my documentation locally. So it says the HTML pages are in build-html. So if I open this up, I can see that there's a bunch of HTML files. So let's go ahead and open up this index.html. So here it is. Here's the documentation. So you'll note that this is local on my machine. So these aren't available for everyone to view, but I can test around and play around with my documentation here without actually pushing to read the docs. So here's how I locally can build and play around with my documentation. Okay, so you can go ahead and play around with your documentation. You can add files, you can remove them, but let's say that our documentation is all ready to go. So what we're going to want to do is actually add these files to Read the Docs. And Read the Docs is the tool that we're going to be using to actually publish our documentation. So you can go ahead to readthedocs.org. And this is the website you'll use in which to publish your documentation. So you can create an account if you don't already have one and you'd like one, but I already have an account, so I'm going to go ahead and just navigate to my account. So in order to add documentation to Read the Docs, you can go ahead and import a project. When you create a Read the Docs account, you can link it to your GitHub, so it will know where to import a project from. So if I go ahead and click on import a project, it will bring up all of the repositories I have. So I can just click on any one of these and it would generate docs. But I already have my Comp Bio Seminar docs here. So I'm going to go ahead and click on these. So this is hooked to my repository, and we can see that the documentation are passing, which is great. So they're building successfully. So now I can also go ahead and click on View Docs. And you can see this link on the top. So these docs are no longer local. These are public for everyone to see. You might also be viewing them right now as well. And so this has all the documentation we've created in this tutorial. And as you update your GitHub with your docs, these will automatically update. So no need, once you've set up Read the Docs, you don't really have to touch it again. The documentation will update as your GitHub updates as well. You might note that we have this API documentation. We've gone ahead and built automatic API documentation using some special Sphinx modules. I'm not going to talk about that today because we're out of time, but information on how to build API documentation using Read the Docs is available on the tutorial. Also, feel free to contact me with any questions you have about building this API documentation or any other questions as well. Just note that this is available functionality and how Sphinx can be used to automatically build some documentation. So here I have some functions, and so it's automatically built information that users can view about how to use these functions. Okay, so that was a lot of content. Thank you so much for listening. It looks like we're about at the hour. All of the resources I've used today are available on the tutorial. So if you are interested in doing something like we've done today, I highly encourage you to go to the GitHub and pull that code. You can play around with it. You can use it as a template for any future projects you use. There is a link on this, on the very last slide, which I'll just put in the chat real quick. And this link is the last slide of the tutorial, and this contains links to all of the resources in which we talked about today. So this includes the source code, how to make Python packages, how to use Read the Docs, how to use Bioconda, how to use PyPy, and then how to use Travis. So these are the most straightforward documentation I could find. So hopefully these extra resources will help you to create your first or 10th Python package.
Thanks so much,
for
Melissa.
listening.
That was fantastic. That was much clearer than any documentation I've ever seen about how to make this kind of Python code public.
Good.
That was fantastic. There's two things I wanted to say. The first one was I also put in a link on the chat to a Google form. It's very short. If anyone has about 2 minutes to spare, could you just go on there and just give us feedback really quick on as to if you found this presentation helpful, as well as what we can talk about in the future. If you have any ideas, we're always looking for new topics for next semester. And the second thing is I'm happy to stay on for another 5 minutes or so, as long as Alyssa is, to take any questions should people have them. Yeah, otherwise, thank you all so much for coming.
Hey guys, sorry, can I ask you a question?
Yeah, of course.
So one thing I've been struggling with, I tried to wrap up some like my stuff into a package, and one thing I do not understand how people do is like the imports. So I saw some packages do like relative imports, some packages do like import the package itself, like globally. Can you tell me about like best practices, like how should I organize that thing?
Yeah, so generally I think, I don't know, Matt actually might have some information, but I think relative imports are good for development, and also global imports can get a little complicated. If you have a tool installed that's some elsewhere, it might actually be accessing the wrong version. So I always recommend doing relative imports. It's usually the best way to do this when you're locally developing your tool and when you publish your tool so that pip kind of knows where the exact file is. Because it does sometimes happen that you have you have the same package installed multiple places, and then it can get confusing. Okay, which file do I want? Do I want the old one or the new one? So yeah, relative imports are the best way to go there, in my opinion.
Yeah, I would agree.
Oh, and one more also thing there, like some project like some projects get divided by folders, where like one folder is for like, I don't know, calculation, one folder is for like plotting or something. I've been kind of struggling like different depending on like version of Python, like this and that, on like folder like imports between the folders. Is there any general recommendation, or it just like depends on specific?
So are you asking like how to talk between the folders?
Well, so I definitely saw this thing where like when I use like Python within PyCharm, I can import like between two folders. When I do like just command line, it hates me and doesn't want to like do that. So like, is there a general way to structure imports between two folders, or is it like not a recommended way to organize into folders? Like, what do you do with that?
Yeah, it's fine to import between folders. I think one thing that's often done is you might have a utility package and you want to reference so these folders you can kind of think of as like mini packages, and you can have a utility package, for instance, in which you reference from your other sub packages. So in our tutorial today, we had plot map q, but we could also have other subdirectories such as maybe called utils or plots. And these are just sub packages that can be referenced by the other packages. So yeah, that's perfectly fine. And I think that's a pretty common way to do it. Some of the big projects are like really nice ways. So the nice thing is all of these Python projects are available on GitHub. So for example, if you see how Python structures these sub packages, it might enlighten kind of how to do that in a straightforward way. But that is the most straightforward way to do things, to keep things clean, especially so users of your package don't necessarily have to import every single file. You'll want to have subdirectories, and these can be imported relatively.
Yeah, and just to add to that very quickly, if you have an init file under each one of these subdirectories, pip will treat them as different modules, as Alyssa said. So you could import it as like home directory, subdirectory, even like another subdirectory. And there are tons of packages that do this, as Alyssa said. So Matvey, if you are curious, I'm sure we can point you to one or two that might be good to look at.
Oh yeah, that would be great. Thank you.
No
Do
problem.
you like, is there any difference? Like, basically I've been trying to develop my thing as much as possible before submitting it to pip. I'm just kind of expecting that like I'll finish it all up, submit to pip, and then once I put it into pip, something will break in terms of like imports and shit, and I'll have to like come back and fix that. Did you have like these problems, or I'm just being like not understanding correctly what, like, how does that work?
All the time, right? Because you have all of these files in your directory, and maybe you forgot to specify in the setup script, maybe there's a dependency you left out. Maybe you didn't specify all of your scripts in the scripts objective. So I think what we talked about today, I would highly recommend first publishing your tool to test PyPy, which is what I use today. So I would definitely not publish it to PyPy before you know everything is working. So
Yeah.
step number one is publish to test PyPy. Step number two is if you use Conda, make a new Conda virtual environment, completely clean. Try installing your package into the clean environment and see if it works. Because often you try installing it and you're like, oh, it worked, great. But other people's environments are different. So go onto a different computer, or create a new Conda environment and make sure you're outside of the directory of your current project to make sure you're not referencing any of the files in your directory. Does that make sense?
Yeah. That's kind of what I was curious about, because I'm a little confused with like how to publish it while also troubleshooting the imports and like dependencies and all this stuff.
Yeah. So number one, use test PyPy. Number two, create sorry, before I say that, have you used Conda before, or Conda virtual environments?
I mean, as a user, yeah. As a contributor, no.
Oh, no, I just meant as a user. So great, so you can make a new Conda environment and try to install your tool from test PyPy. And so that should be the best way to isolate whether it's actually working or not.
Okay, thank you.
Yeah.
Any other questions? Yeah, it's tough here. I can't see anyone's face. I don't know if you're on the verge of asking a question or not. So sorry if I am missing you. Okay. Well, Alyssa, thank you again so much for joining us and giving us that great seminar. As she said, all the resources are online on our home website, ccbskillsem.org or .com. I forget what it is. It's in the chat. And then this video will be posted as well. So for your own viewing pleasure. Yeah. Cool. Well, thanks again. We have one more seminar this semester in December where Adam will be leading it about ScanPy and SEI. Cool.